The objective of this video is to show how the vector potential can be used to determine machine flux paths. We previously talked about how in 2D FEA, the vector potential is the fundamental quantity that is calculated. Usually in our analytic derivations, we don't much worry about the vector potential, but the FEA approach inherently calculates the vector potential as part of its solution. And it turns out that we can use the vector potential to quickly determine the machine flux paths, as well as the total flux through surfaces. And that is what we're going to develop in this lecture. So if you recall, the total flux through some surface can be calculated as the surface integral of b.ds. So again, this is analogous to current, where current is the integral of current density over a surface. Flux is the integral of flux density over a surface. And we talked about previously how we can define a vector potential, which is what is used for FEA calculations, where the curl of our vector potential is equal to our magnetic field. So if we plug this into our expression up here, we get the following integral. And then we can use vector calculus properties to rewrite this as this integral, which is a dot dl along a closed path. And so at first pass, this doesn't appear to be much of a novel development. We see that we can calculate our flux based on our kind of conventional approach of the integral of b dot ds. And now we have this new option where we can calculate it as a line integral of a along the surface, along the contour that bounds the surface that we're interested in. It turns out that in 2D FEA, this is actually quite a useful calculation approach. Because if you recall our assumptions for 2D, we say that the only non-zero component of A is in the z direction. And we also say that that component does not vary along the z-axis, because we're only solving the fields within an xy contour. So let's consider the following example. Suppose that we want to calculate the flux linkage of some coil. And I'm going to label our x, y, and z axes here. And let's assume that the coil extends axially in the z direction, and then it has some extent in the radial xy plane as well. So that we end up with this rectangular surface that we're going to calculate our flux linkage of. And this coil extent in the z direction has a length of L. So we could calculate this either by manually integrating the flux that flows through the surface. So if we had our field flowing through the surface, we could integrate that manually. Or we can try to evaluate our vector potential along that contour. And we're going to take the vector potential approach. So we'll pick a path like this. And this path implies that flux traveling through our coil in this direction is positive. Okay, let's do this one segment at a time. Along this top portion of the coil, we evaluate a dot dl, and we find that it is equal to 0. Because remember, we only have the only component of A that is non-zero is in the z direction. And so that portion of the coil is in the xy plane, and there's no component of A that is in the x or y direction. And we can say a similar thing down here. Okay, next, let's pick the left-hand side. So we'll evaluate a dot dl along this contour. And here we can see that this involves the z direction component of A, and that is non-zero. But we've said that the derivative of az in the z direction is 0, so it's a constant. It comes outside of our integral. Let's define this point right here as a point 1, and we'll call this as point 2. And so we can say that this is equal to the az component at point 1 times the length in the axial direction. And then we can do a similar thing on this side. And now we're going in the negative z direction, so we'll have a negative az at point 2 times our length. Finally, if we write this all out, we can say that phi is equal to a dot dl along this closed path, which is simply equal to a at point 1 minus a at point 2 times our length in both cases. And if you've done yourself with an FEA tool, this is a very simple calculation to make. All you have to do is sample your vector potential at these two corners of your coil, and suddenly you know the total flux that's linking your coil. And we can expand on this to make another interesting observation, which pertains to the flux plots that we see in our FEA tool. So suppose you have the following very simple geometry. You've got a permanent magnet rotor that has, of course, a north and a south pole. And then outside of your rotor, you've got your stator. And so what I'm shading in right now is the steel portion of the stator, which is going to tend to carry our flux. And in between the rotor and the stator, of course, is our air gap of our machine. So if you do a simple FEA static solve of this, the first thing you typically do is you tell your FEA tool to show you the flux plot. And the flux plot is a contour plot. And you'd see something like this. Now I guess, let me see what color. I'll sketch this in blue. You'd see a set of contours. And you'll have to excuse my drawing. And your contours will kind of wrap around like this. And you'll be creating this yourself soon, so you won't have to rely on my limited drawing ability. And depending on your settings, you may see many different contours, or you might see only a couple. And by settings, I mean how sensitive you make your contour plot, how many of the levels, how many of the contours you want to have displayed. So you'll create a plot like this, and typically you'll show more contours than I'm showing. And each of these contours represents a contour of constant vector potential. And why is that interesting to us? Well, it's interesting because of what we just noticed above here. If you have a contour of constant vector potential, if the vector potential has the same value at all points on a line, that means that there's no flux that crosses that line. There can't be any net flux because having flux cross that line implies that you'd have different vector potential values. That's what we just proved. And so this means that H and B do not cross these lines. That is, H and B must be parallel to the lines when you're sufficiently close to the lines. And that gets to the second part of this. These are called flux lines because they're showing you the path that flux takes, that flux or field takes equivalently. This gives us insight into the flux tubes or the reluctance paths of the machine. So we've previously talked about this notion of reluctance elements or a magnetic equivalent circuit being analogous to an electric circuit. In an electric circuit, you have current paths with resistances, and the resistance represents a path that the current takes, which is in some material, and you could call it a current tube, perhaps. And similarly here, our magnetic field takes a path, and it's bound in between these lines. So there's field that's flowing between these lines that does not cross the lines, and we call this a flux tube. And we can use our reluctance calculations that we developed in our previous video to calculate the equivalent reluctance of this, and we can say that we can draw it as if it's a resistive element, but we label it with the script R instead. So these lines are contours of constant vector potential, and they are also lines that bound flux tubes, or they bound the flux paths. And that concludes this video. In summary, we've shown how the vector potential can be used to determine machine flux paths. And we've developed this from the definition of the vector potential and the definition of flux as being the surface integral of our flux density over a surface. We've given an example where we calculated flux for a coil by using the vector potential. And then we discussed how to interpret the contours of constant vector potential in the cross-section of our machine within a 2D simulation.